So this is joint work between me, my fellow PhD candidate Simon, and our supervisors Henrik and Magnus. And I'll present the algorithm that. Oh, sorry. Oh, this was sensitive. There. I will present an improved version of the algorithm that won the IRP track of the 12th DIMACS implementation challenge. And the underlying idea from this method comes from the work of Simon in his two last papers, where he used an improvement MIP to improve a feasible solution of the IRP. And we wanted to see if we can formulate a new improvement MIP that explores a large enough neighborhood to find good solutions without becoming intractable to solve. And then secondly, we wanted to see if it's beneficial to embed this improvement MIP within a branch and cut method. And spoiler alert, the answer to these questions is yes. And I guess, as we've seen these last days, most people here work closely with CVRP and VRP with time windows. So I'll just do a quick recap of the IRP, what it is. And I was lucky enough to borrow a very nice animation from Simon. So in the IRP, we have to plan over a planning horizon of, or a finite planning horizon of discrete time periods. And we have a single depot with a set of customers. And they all have their inventories. And they have the customers, they have a demand in every period. And at the depot, at every period, it becomes available some homogeneous products. And then we have a homogeneous fleet of vehicles to service all these customers. Yeah, so we basically have to deliver enough products so that the inventories never exceed their limits. So we can just have an example of what happens in the first period. We load the vehicle, and the vehicle goes around here visiting all the customers that are about to run out of products. And then we update the inventories, and we can move on to the next day, and we have to have a plan for that day as well. And yeah, and then we get to a next period, and we get like an updated inventory balance at each customer and the depot, and we can execute the next day's plan. So in the IRP, we have to make three simultaneous decisions. We have to decide when to visit a customer, how much to deliver once the customer is visited, and how to route our fleet of vehicles such that we minimize the sum of the transportation costs and the inventory holding costs. So I'll just jump right into let's say the overall or the top architecture of our method. It's very simple. We start with constructing a feasible solution, which we give to an improvement heuristic. That the main component is this improvement MIP that tries to improve this feasible solution, and then we warm start a branch and cut method with this feasible solution. And if the branch and cut method finds a better solution, we pass it back to the improvement heuristic to see if we can find any further improvements. Yeah, so now I'll just jump straight to the results before we go more detailed through the content of these components. And here we compare our results on the rightmost column here with the state-of-the-art results in the literature. And we report here the best known solutions as the first figure. And in the parentheses, we have the number of unique best known solutions. So that the method has, this is the only method that has these 16 best known solutions, for example. So we see that our method performs pretty well. We have a total of 741 best-known solutions and 247 uniquely best-known solutions out of the benchmark instances. And I think the only exception is the small set of instances with 2 vehicles where we are slightly worse than the branching cut of Guimarães et al. And if we compare the computational times, we see that we just compare on the 307 instances that are solved to optimality by all the exact methods we compare with, just to not skew the averages too much. And then we see that on average we're slightly slower than the other 2 exact methods here, but we are faster on the 4 and 5 vehicle instances. And I think this comes from the fact that the improvement heuristic is it's based on a path flow formulation. So as we've seen earlier this workshop, that path flow formulations usually struggle when you have few vehicles that do long routes. So I think this is part of the explanation that it takes a lot more time for the smaller vehicle sizes. And then we here have the comparison on the DIMACS instances with the solvers that were submitted to the DIMACS challenge. I think this is ranked from last place to first place, where this is the solver we won the competition with, and then this is the improved version. So we've done quite substantial improvements since the competition on this project, which was nice to see. I think that's enough. I'll just quickly go through the construction heuristic. It's not the main component of the algorithm, but it's needed to have a starting point. So we use two heuristics to create a set of promising routes, and then we solve a path flow model that just selects the best set of routes we can find and distributes or adjusts the delivered quantities among the customers. And we use just a commercial MILP solver to solve this path flow formulation. And we stop either when we reach optimality or we reach a certain time limit. So this first route generation heuristic, it's quite simple. We create a giantor, which is basically the TSP solution of the graph, except for the depot. And we assign delivered quantities to the customers to be a predetermined percentage of each customer's inventory capacity. So we start at 80% and we iterate slowly, like through 16 iterations with decrements of 2.5. And then for each giantor we get, we use the splitting algorithm of Vidal to generate routes, and then based on these routes, we get this pool of routes that we can again use in the path flow formulation. And then the second heuristic for generating some initial routes are that we assign delivered quantities to the customers such that as many customers as possible with the same demand pattern are visited in the same periods. And here by demand pattern, we mean customers that will run out of inventory in the same period if you do nothing, more or less, like roughly speaking. So then once we have determined these delivered quantities to all customers, we use the hybrid genetic search algorithm from Vidal to solve a set of VRP instances. And again, we end up with some initial routes that we can choose from. And now we get to the interesting part, which is the improvement heuristic. So the biggest improvement since the challenge is to to come up with a brand new formulation that generalizes customer insertion and customer removals from the initial route pool, let's say. And we solve this improvement MIP several times, either until it converges, so it doesn't find any improvement from one iteration to the next, or until we reach a maximum of 5 iterations. And the key property of this improvement MIP is that we have an exact evaluation of the cost of the route modifications we do, so that any proposed modification from the model will be improving for the original problem. So let's just have a, I won't go through the formulation and all the notation, so we'll just have a quick overview of like what type of modification the model allows us to do. So we start by, like in any path flow model, selecting a set of routes, but on these selected routes, we allow for some customer insertions. So we allow for inserting clusters of customers with cardinality 1 to 3. Here I see something messed up with my animation, but never mind. So if we start with the let's say cardinality of 1, in this example, we have 3 potential customers that can be inserted to the route. And then we pre-process by calculating the cheapest insertion cost for each cluster. In this case, it's singleton clusters. But we predetermine that a cluster can only be inserted in the cheapest insertion position. So in this case, customer 9 can only, let's say this is the shortest or cheapest insertion, it can only be inserted here, because not to make the model too intractable. Like it's a measure to try to keep it easy to solve. And we do that for all clusters. So also like clusters of size 2. And the same for clusters of size 3. And in addition to this, we allow for customer removals of clusters of cardinality 1 to, here it says 4, but it should be 3. But we can only, in the removal, let's say, operator, we only allow for consecutive nodes to be removed. So either like singleton clusters, like either here 3, 8, or 2, or we allow for the cluster of 3 and 8, or 8 and 2. Or we can, in this case, remove all of them, but that doesn't really make sense in this case, because then we could just not use the route in the first place. And to keep this property of exact cost evaluation, we need to, or we impose that if you remove or insert clusters of customers in a certain position, the nodes prior and after to that insertion or removal has to be present in the route. Sorry, has to be present in the route. To calculate or to get an exact cost calculation. And this, like on this example, like where we have this route here, we can get a wide range of possible routes with these simple modifications. And now you're probably thinking, why are we using MIP to do this? Because most of you probably have a local search that could do this much, much faster. But I'll try to give some intuition to why this actually works. And so let's assume this is a feasible solution to a 3-period instance of the inventory routing problem. And typically, like in the CVRP, let's say, it has this kind of binary property, right? Like if you use some operator on this solution, it's either just is it feasible to do this this operation or this move or not? Like if we swap 5 with 4, for example, or 5 with 2, for example, here, is it Is it feasible? Yes or no? Is usually the unless you have some recovery mechanisms for infeasibility and stuff. But like simply speaking, it has this binary property. But the inventory routing problem doesn't, because here it could be that inserting customer 5 into the route here is possible, or it's improving the solution, but only if we readjust all the delivered quantities in the remaining customers, and maybe also we need to add another visit in another period to get the improvements. And as far as I'm concerned, I haven't found any pure meta-heuristic that is capable of finding these kind of moves, because it's kind of like to find improvements in the IRP, you kind of need a union of moves to actually find the improvements. And that's what, as long as you keep this improvement MIP keeps it relatively simple to solve, it's very good at finding these kind of improvements, like to do insertion and removals and adjust the delivered quantities in such a way that you actually find the improvement. So we can have, am I running out of time here? I can keep going a bit more. So this graph here gives us a bit more insight to how much of these kind of operations do we do, or how much modifications do we do to these initial routes that we find. So here we have an overview of classes of instances ranged by number of customers. So we separate here between the small and the large instance sets. And here we have insertions of cardinality 1, 2, and 3, and removals of the same. And we see that we do quite a lot of insertions and removals of cardinality 1, and then gradually less and less of the higher cardinalities. This is also why we just kept it at cardinality of 3, because we could have extended it, right, and included insertions and removals of cardinality 4 or 5 or whatever. But it looks like it's like a diminishing trend here. Like the greatest benefit seems to be from the insertion and removals of single clusters or single customers. And then the branch and cut method that we used, it's a slightly modified version of the one that is proposed in my paper from 2022. And this customer schedule formulation is just a Danzig-Wolfrey formulation of a subregion of the feasible area, where the customer schedule contains information of which periods a customer is visited and the delivered quantity in each of these periods. And then we can get an interior point representation where we take convex combinations of these customer schedules to represent the feasible region. And the modification we did on this formulation is very subtle, but it drastically reduces the number of customer schedules at the cost of potentially weaker impact on the dual bound when branching. So I think I'll just skip through that now. The details can we come back to if someone is interested. But yeah, the detail is changing the equality sign of a set of constraints to greater than equal, or greater or equal than. So let's go back to this architecture here. And we wanted also to figure out if it's beneficial to embed such an improvement heuristic within the branch and cut method. So we did some analysis here to check how often is this loop here called, like how often does the branch and cut method find an improvement, and also how often does the improvement heuristic manage to further improve such a new best solution. So here we have a graph, a lot of numbers, but I'll try to explain. So in this column here, it's the number of, or it's the same here with like we have the instances of the number of customers. But this column here reports the number of times the branch and cut method called the improvement heuristic. So a number of times we used this arc here. And from those branch and cut, or from those calls within the branch and cut, we found here the number of improvements. So like the number of times the improvement heuristic managed to improve the new best known solutions from the branch and cut method. And finally, we see how many instances does that relate to. So it's not like there is just one instance that it managed to improve a lot of times. It's actually across quite a lot of instances. Like, around 10% of the instances, we had a benefit of using this loop between the branch and cut and the improvement heuristic. And then this last block here, it's just showing the relative improvement in each iteration of the call. So between each iteration here, like so at maximum it called this loop 4 times in our tests, and it's like diminishing improvements, of course, because we're getting gradually to a better and better solution. And then we also did some modification and tested this on the split delivery vehicle routing problem. So, and that's quite interesting problem because it's a special case of the IRP, but it's also a relaxation, right? Because you can visit a customer several times. So we have the same domain as for the IRP, or variable domain, but where customer visits are integer, and same with the arcs out from the depot are integer, and otherwise it's the same. So also the improvement MIP has to be adjusted slightly, like you have to allow for more visits, but other than that it remains quite the same. So it was interesting to see, okay, does this also work for other routing problems? But yeah, using the same branch and cut model, which is a 2-index vehicle flow model, it makes it becomes a relaxation for the split delivery VRP, because not having an index vehicle on your arcs allows you to do transshipments. So we add feasibility cuts dynamically to avoid solutions with transshipments, and these are the same cuts. I forgot to put the reference, but it's the same feasibility cuts as was proposed by Archetti et al. I don't remember exactly the year now, but yeah. So this is basically saying that if you have a solution K that is feasible for the relaxation of the split delivery vehicle routing problem, but it's not feasible for the actual split delivery vehicle routing problem, we say that all the arcs that were not in that solution has to be greater or equal than 1. So we force, and we cut off that exact solution basically. So quite straightforward. And unfortunately, it doesn't perform as well as for the IRP, but still quite decent. So here we have gathered all the state-of-the-art methods we could find in the literature. And we see here that the He and How paper, or like the heuristic they proposed in 2022, it's clearly the best method in finding most best-known solutions. But we come in on a close call for a second here. So I would say it works decent on the split delivery vehicle routing problem also, but it's not as impressive as for the inventory routing problem. Yeah, I think that's it. So if you have any questions. Oh, one comment that the preprint is available at axiomresearchproject.com, also with all solutions, detailed solutions published. So if anyone is eager to test their local search or whatever on this problem, you're free to go. And yeah, there we also have published a preprint on new instances for the IRP as a complement to the original benchmark instances. So if you'd like to take a go at this problem, it would be a good place to check. Yeah, any questions?
Any questions for Jørgen?
Yeah.
Do you do any work on lower bounds for your branching?
Yeah, a bit. Like we have some cutting planes. Like we use the capacity inequalities from the Solniers et al. So they are like a generalization of the rounded capacity inequalities for the CVRP. And then we use what is called disjoint route inequalities from Avella et al., which are also quite powerful for the unitary routing problem. But still, I mean, it's a much weaker formulation, right, than the CVRP, because you have this very weak link between delivered quantities and visited customers. So you won't typically see as strong a bound as you do for the CVRP. Yeah. Any more questions? Yeah.
So how many customers were in a typical route for one of the larger problems? Did you have a sense of that?
Oh, I think quite a lot, because these instances have a bit of a strange structure. Like they were originally published for the single vehicle problem and then later been adapted. So I don't recall exactly now, but I think it could easily be like 50 customers in a route.
Because that would affect the number of kind of insertions.
Yeah. Yeah, exactly. Big routes. Yeah. Yes, that's why also because they also published a branch price and cut for this problem, and that one performed very well on 4 and 5 vehicles, because then the vehicle capacity is relatively small and you have short routes. But for 2 and 3, but especially 2 vehicles, the routes become very long. I mean, like you can, at least for the 3-period instances, you can service all customers almost in just 1 period. So it's a bit. Have some strange structures, these instances, but it's as a result of originally being just developed for a single vehicle problem. Yeah, thank you.